Accuracy only counts who cross the 0.5 line. Calibration asks whether the probability means what it says. These two classifiers can label the same cases and still tell very different confidence stories. In this synthetic example, we control the whole population with a seed. A hidden score becomes a true probability, and then we sample labels from that probability so the experiment is repeatable. Model A copies the seeded probability. Model B keeps the same threshold decisions, but pushes every number away from 0.5, so a 0.72 becomes something like 0.95, and a 0.28 becomes 0.05. A reliability diagram bins predictions, then compares the average predicted probability to the observed fraction in each bin. Points on the diagonal are calibrated, points above or below show a mismatch. The Brier score is the mean squared probability error. Every forecast pays for distance from the outcome, so a confident miss hurts far more than a cautious miss with the same label. Here is one concrete failure. Model B says almost 0 for a case that turns out positive. That row contributes almost a full point of squared error, while 0.45 would have been much cheaper and produced the same wrong label. Because the threshold decisions stay the same, both models get the same accuracy. But Model B makes stronger probability promises and pays a worse Brier score. Same labels do not imply the same calibration. Calibration does not change what counts as positive. Thresholding answers yes or no. Calibration asks whether a number like 0.8 is right about 8 times out of 10. They're separate jobs. The workflow is simple. Keep the test set untouched, read the reliability diagram, compute Brier, then inspect confident misses. Accuracy alone cannot tell you whether confidence deserves trust. Ship labels for decisions, but calibrate probabilities for trust. The winning model is not just the one with the most correct labels. When probabilities matter, its confidence must match reality.